Hello, everyone. Welcome to our presentation for the Capstone Senior Design Expo, representing the Powertrain subteam for the Long Endurance Platform UAV project. My name is Anthony Lee, and with us, we have our team lead, Brandon Santos, Miguel Cervantes, Eric Leone, Ruben Murillo, and Alex Maxwell. We would like to thank Dr. Yarbrough from the Aerospace Corporation for giving us the opportunity to work on this project, and our advisor, Mario Medina, for aiding us throughout the year. The scope of this project as a powertrain team is to create and assemble an efficient powertrain architecture concept. The architecture will be utilizing a power regeneration technique in order to sustain its fuel efficiency. This UAV will also gain sufficient power so that it can maintain flight for 4 to 12 hours. And the UAV will have enough power so that it can meet with the onboard system's requirements. So what is a hybrid powertrain? A hybrid powertrain is a configuration that consists of certain components so that it can convert power from the engine and turn it into mechanical motion. So how will this powertrain be utilized? A hybrid powertrain will be used to provide the UAV ample power for ascend, descend, hover, and forward flight. It will also provide enough power in the UAV's onboard infrastructure. The UAV will undergo regenerative power so that the drone can maintain a longer flight time. The significance of having a UAV with a hybrid powertrain when comparing to the current UAV market is that the current UAVs in the market typically contain one power source. Our UAVs utilizes two different power sources, one being the battery pack and the other one being the use of fossil fuel. So due to the COVID-19 pandemic, the team ended up having no access to the makerspace. So seeing as though we are unable to go on campus, the team ran simulation on Simulink, one of which is doing a graphical approach on the brake-specific fuel consumption of the selected engine. We optimized efficiency where we designed a gearbox layout and made a hybrid flight cycle for hover. We update and change any component's specification if they fail to meet with the system requirements and troubleshoot all the issues during the simulation. And now I would like to pass this presentation along to Ruben.
Thank you, Anthony. I will now be discussing the three different types of architectures commonly used for hybrid powertrains, beginning with the series configuration shown here in Figure 1. The series is the simplest design as it has direct connection to each component. For this proposed model, a gasoline internal combustion engine acts as a prime power plant, driving the generator, which then provides power to the motors and the energy storage system. Through this process, there are a lot of energy losses, thus highlighting one of this architecture's main drawbacks, low efficiency. Additionally, in this configuration, the engine is small, since it only has to deal with the average power demand. However, this means that batteries and motors must compensate for the peak power demand, thus making them larger, which means the architecture as a whole tends to be on the heavier side of the three configurations. The function of the electric motors and the hybrid electric propulsion system is twofold. It may act as a supplementary power plant to the internal combustion engine when required, or as the sole power plant to the UAV. The generator and the electric motors are physically the same machine. However, it is assumed to be the reverse of the electric motor. Its main purpose is to provide the battery pack with charging current when this extra torque is available in the propulsion system. Now, the battery supplies current and voltage to the accessories on the UAV and also to the electric motors when it is activated. Moving along, we have the parallel configuration shown here in Figure 2. This architecture allows for the powering of the UAV by using the internal combustion engine alone, the electric motors alone, or a combination of the two. For this configuration, electric motors are able to provide extra power during acceleration and recharge during deceleration through regenerative braking. In this regenerative braking cycle, the generator charges the polarity of the internal combustion engine and thus provides energy for the battery pack. In comparison to the series configuration, it has a slightly better efficiency and is lighter in overall weight. Lastly, we have the power split configuration, also known as a series parallel configuration, as it has elements from both the series and the parallel. This configuration lacks a driveline clutch but utilizes a power transmission like a gearbox to transfer power from the internal combustion engine and electric motor to the propellers. The engine delivers torque to the propellers after splitting a portion to a generator for conversion to electricity. The electric power recombines with engine mechanical power at the gearbox. Since the combustion engine power and speed are decoupled from the overall propulsion demand, the engine is able to run at near optimum demand, Compared to the previous two architectures, it is the most efficient, has similar weight, lowest fuel usage and emissions, and for these reasons, it was chosen as a desired architecture. I will now pass it over to Eric to continue the presentation.
Thank you, Ruben. And now we'll be going over the displayed mechanical layout, which is specific to the power split hybrid system, where we're taking the thermal energy from the fuel tank and converting it into mechanical power with the use of an internal combustion engine. This mechanical power will then be converted into electrical energy by the generator, which will power the battery management system. The battery management system, shown in the middle of the layout, is a key component to this architecture. It will control the power directed to the electric motors, propellers, ducted fan, flight controllers, and any sensor within the UAV. The key component is powered by the battery pack module shown below the battery management system. Next, we will cover the procedures of Design 1, which are the following: the architecture trade studies, the concept design developments, the component selection, and the optimization of the powertrain. To get started, we will cover the desired function requirements that the powertrain set out to complete during the first design. A few things to note are the weight allocation and the time flight range. The allocated weight was not met due to the addition of a generator and the consideration of a gearbox. The flight time range was met for a minimum of 4 hours due to the fuel consumption of the engine. Next, we have the engine considerations for Design 1, which are the following: the RCV engine, desert aircraft engine, and the power for flight engine. The criteria taken into consideration during the selection process was the power output of the engine, volume of the engine's weight, and the amount of fuel the engine would consume. The starting point for the power requirement was of 3.4 kilowatts for hover, which shown here, all engines meet that requirement. Although all the engines meet the hover requirement, the powertrain team required an engine that can meet the requirements for hover, ascend, and forward flight at the same time. Therefore, the engines by desert aircraft and power for flight meet this specific criteria. The distinguishing factor that allowed the powertrain team to select the engine by power for flight was the power output of the engine and the engine's BSFC. As shown in Table 2, the power for flight engine has the lowest BSFC out of the 3 engines. The BSFC of an engine is the amount of fuel it would consume to produce a unit of power per unit of time. This parameter allowed the powertrain team to calculate the amount of fuel consumed during a specific time of flight. And now I'll pass this presentation to Miguel.
Thank you, Eric. As shown on Table 3, the selection of the generator for the powertrain design consists in the A-propelled generator and Sullivan generators -1, -3, and -7. The generator must be capable to operate within the RPM range from the chosen B150i engine. Therefore, as shown on the table, the A-propelled, the Sullivan-3, and Sullivan-1 are capable to operate within the B150i engine RPM parameters. However, the A-propelled does not need to operate at its maximum RPM range, since it has a range between 2,000 to 9,000 RPMs, where in comparison, the B150i engine has an RPM range of 1,100 to 7,000 RPMs. Additionally, the A-propelled and the Sullivan-3 are capable to generate more power in comparison with the other two choices, where the A-propelled can generate a maximum of 8,500 watts and Sullivan-3 can generate a maximum of 11,400 watts. All 4 iterations seem very similar in their dimensions. However, with an effort to save weight, the A-propelled was the lighter option with a total weight of 5.4 pounds. Therefore, the A-propelled was the chosen generator for the powertrain design. The chosen engine and generator for the powertrain design was the 2-stroke B150i engine and the A-propelled generator. From this combination, the engine and generator are capable to generate the necessary power for all electrical components, since the generator fits within the operating RPMs and power parameters from the engine. Additionally, this combination also fits within the volumetric constraints when placed inside the duct of the UAV. Furthermore, as the project evolved, the power requirements increased, and then a planetary gearbox was designed with an effort to maintain the engine at its optimum RPMs and still generate the required power parameters. This means that the planetary gearbox would allow to have a better fuel consumption during takeoff, hover, and flight. As shown in Figure 6, a planetary gearbox consists of a ring gear, a sun gear, and a carrier that is attached to planetary gears. For planetary gears to be functional, One component needs to be held, and the remaining two components are used as an input or as an output during the transfer of power. Moreover, planetary gears are usually compact, they are lightweight, and they usually have a 97% efficiency. During the first powertrain design, it was chosen to have the engine shaft pointing directly towards the ducted fan of the UAV. For the planetary gearbox to be functional, as shown in Figure 7, the gearbox needs to be placed between the generator and the fan. This means that the engine will now serve as the input delivering power to the output gear of the gearbox towards the fan. The gearbox option 1 consists of a step-down gear, where the RPM of the ducted fan required for hover is lower than the RPM of the engine to be able to stay under optimum conditions. From Table 4, the required RPM for hover is approximately 3,553 RPMs. The gearbox design was capable to reduce the necessary 6,500 RPMs to 3,900 RPMs delivered to the ducted fan. This is an approximately 10% difference from the required RPM for hover and the RPMs delivered from the gearbox. For this iteration, the gearbox was designed to utilize the ring gear as the input and the carrier as the output. As the project developed, and for better structural and allocation purposes, it was decided to flip the engine and use an electric motor to power the ducted fan. Therefore, the gearbox purpose would now function to make more power out of the engine, but still maintain the engine under its optimum RPM. This means that the gearbox would now be placed between the engine and the generator as shown in Figure 8. For this iteration, the gearbox functions now as a step-up gear, where the generator optimum RPMs are greater than the 6,500 RPMs from the engine. This allows to maintain a better fuel consumption, but also generates more power. As shown in Table 5, the design gearbox was capable to increase the RPMs towards the generator to approximately 8,600 RPMs. This is 5% difference from the maximum operating RPMs from the generator parameters. With that said, now I would like to pass this presentation to Eric.
Thank you, Miguel. Up next, we'll be going over Design 2, which entails the requirements that were changed and met during this new design process, the comparison of Design 1 and 2, the component selection for Design 2, and we'll also go over the flight analysis, the power management network, the battery pack alternative that's under consideration, and the engine assembly. Furthermore, we have the functional requirements that the powertrain set out to complete during the second design. Some key differences between the previous functional requirement and the current one are the weight, the volume inside the duct, and the power demand from the engine. Previously, we had a weight limitation of 20 pounds, which we later found out was not enough for our engine and gearbox. The volume changed due to the increase in diameter of the duct for our new design. The power demand increased due to the increase in weight to the entire UAV design. And lastly, we were able to determine a time of flight of 7 hours with the use of the BSFC of the new engine. Up next, we have the comparison of the previous design to the current one. Some important features to point out here are the new power demands of 7 to 14 kilowatts for the current design. The generator is now integrated within the engine, and currently there is no need of a gearbox. Also, with the new engine, we have an area decrease, which means an increase in flow through the duct and an increase in thrust. Moving along, as stated earlier, we wanted to compare the engine of Design 1 to that of Design 2. The BSFC graphs presented here in Figure 9 allow that visualization of that comparison. Each engine was analyzed at 3 distinct points, and the selection of these points was done with the power for hover in mind, along with which point would provide the best time of flight for an engine-only scenario. Thus, the following table shows the values obtained for the power for flight engine. Each point was categorized in terms of BSFC and flight time. The worst case provided 3 hours and 31 minutes at a BSFC of 308 grams per kilowatt hour, and the best case provided 6 hours and 42 minutes at a BSFC of 284 grams per kilowatt hour. The Sky Power engine was categorized in terms of flight time and BSFC as well, with the worst case providing a flight time of 1 hour and 56 minutes at a BSFC of 245 grams per kilowatt hours, and the best case scenario providing a flight time of 2 hours 47 minutes at a BSFC of 362 grams per kilowatt hour. And now I'll pass this presentation over to Brandon.
Thank you, Eric. In the next few slides, I will be presenting information based off the battery pack selection. I will be using that information and the engine information provided by Eric to take you on a journey towards the development of a hover flight analysis, iteration, and power management network. The Gray Pal Tattoo 3.0 Plus is a lithium polymer-based battery cell design. The cell arrangement consists of 14 cells in series and 7 in parallel. This is a key structural design in ensuring the ability to run at a high voltage and allow for sufficient discharge of flight vehicles such as our own. The initial trade study prioritized the sizing of our component specification requirements and usage type. Then the dimensions and weight were sized by calculations and verified with the findings of this on-the-market item. The operating temperature is something to keep an eye for in the thermal analysis considerations, which will be one of the primary reasons for the battery placement we chose on the powertrain. The important takes here include the high voltage at 51.8 volts, the 19 amp hour rating, the 150 amp continuous current, the 57 amp recharge rate, and the 500 cycle life counts. These parameters are used to find necessary items such as flight time, flight power requirements, and limitations. The battery pack does come with an integrated battery management system, which comes with operational system sensors shown in this bullet point. Being able to monitor the battery's operating conditions is integral in ensuring the passage of safe and successful flights. Onto the power management network, it was vital to the success of our design to be able to identify the power, voltage, and current requirements of our UAV. The first two tables show the flight propulsion components comprised of our ducted electric motor and outer mini electric motors, whilst the onboard systems consist of key flight system components and sensors that are necessary for sustained flight and observation. The idea here is to gather the total power, current, and voltage consumption. From the power consumption total and the BSFCs previously mentioned from our engine performance, we can extrapolate the total flight time while abiding to our fuel tank volume constraint. From the battery's amp hour rating and current total, along with its recharge rating, we can use this information to properly develop a load and unload cycle for the hybrid system. The voltage differences are important to highlight because in order to properly run this UAV, there needs to be voltage splitters in order to channel the necessary current to each component. In Figure 13, I will be going over one complete hybrid cycle. Phase 1 consists of having the battery on and engine off until 50% of the battery is discharged to power all components in the UAV. In Phase 2, the engine/generator turns on and the battery turns off, and the 50% recharge is initiated. Once the charge is returned to 100%, we return to Phase 1, thus completing one hybrid cycle. We use this strategy and conduct an analysis shown in Table 12. By using the fuel tank volume as our limiting factor and the BSFC value based off the power requirement, we estimated a 3.5-hour flight time provided by the engine. Battery flight time based off the aforementioned performance parameters yielded a 3.5-hour flight time as well, thus providing a total flight time of about 7 hours at roughly 50-50 fuel to battery ratio. In Table 13, a hybrid cycle is broken down to display the battery discharge and recharge times based off the fuel flight time limiting factor, which is then used to find the amount of hybrid cycles that can take place in one flight, which is 21. Recalling the battery pack's life cycle of 500 and using the information for the cycle counts of one flight, the last column shows that we can achieve 23 flights before the end of life cycle of the battery pack module. This is a graphical representation of the number of cycles allowed for in hover flight versus the fuel and battery percentage over cycle time. Because we have constant power demand at hover, the fuel percentage decreases in a linear fashion with horizontal pauses, which indicates when the engine is off, thus causing the red fuel percentage line to produce a step-down pattern. This graph is morphed with the battery percentage discharging from 100% to 50% when the fuel percentage is constant, while also showing how the battery percentage recharges from 50% back to 100% as the fuel percentage decreases linearly. I wanted to close with showing a theoretical representation of the flight system network's wiring diagram. The important thing to note here are the two options for power distribution, which are depicted as yellow block diagrams. The battery pack is shown powering all the main system components, such as the flight control unit, the ECU, and the engine's operating sensors, as well as the electric motors and onboard systems. Then powering off, allowing for the generator to power all systems, while also recharging the battery. Now I'll be passing it along to Alex to expand on the battery trade studies.
Thank you, Brandon. When it comes to choosing a battery pack for the vehicle, there are a couple of options available. Commercial off-the-shelf devices and custom-made products, each of which have their own advantages and disadvantages. With commercial off-the-shelf products, as the name implies, are readily available and can ship immediately from any number of vendors. As such, they're about as plug-and-play as it gets for a battery pack. However, because the packs aren't assembled by battery manufacturers, such as LG, Samsung, or Panasonic, and are instead built by third-party vendors whom are seldom known. Legitimate cells cannot be guaranteed because many, if not most, of these third-party vendors in turn repackage those cells with their own heat-shrinking battery wraps. In some cases, these new wraps are identical to the manufacturer's wrap, such as part and lot numbers, but are in fact cells of an unknown origin with drastically reduced performance than those cells from known manufacturers. Pack connections aren't configurable for a custom solution. Series, parallel, the physical arrangement of the cells, thermistor placement, if any. And if a BMS is included, they offer little or no communication nor configuration, and they are often lacking features desirable for a long-lasting battery. Another alternative for a battery pack is constructing one in-house or outsourcing the construction to a reputable vendor. Either way, a custom pack can be made with features and performance required for a high reliability pack, such as one for an autonomous, long-range, and high-endurance vehicle. Authentic cells can be verified, and the latest technology can be readily implemented where a commercial off-the-shelf vendor would need to assemble and coordinate getting this new product to market. Also, a custom battery management system solution can be implemented, allowing flexibility in adjusting and fine-tuning BMS function, communications to and from other on-vehicle controllers, and therefore can be easily modified via software by another controller on the fly or while the vehicle's on the ground. One example of a custom BMS solution is the Texas Instruments BQ76952. It can monitor a wide range of cells in series and provide critical protection for all cells connected to it. Battery protections include overcurrent for both charging and discharging, short circuit detection, over and under voltage protection, and over and under temperature protection, all of which are needed for any battery chemistry, but are especially critical for those lithium chemistries prone to destructive failure if misused. In addition, it can balance cells in the pack either autonomously or manually via communication with an external controller. It features high side charge and discharge FET drivers built in, which would otherwise require additional components needed to operate those FETs. It offers a suite of communications protocols, which can be used for external controller reporting and on-the-fly modifications if required. And it has multiple additional ADCs and GPIOs, which can be used for additional current and voltage monitoring, additional communications interface, and multiple thermistors, which can be placed strategically within the battery pack for temperature monitoring. Here's an example BMS setup for a proposed battery pack. There are 13 cells wired in series to achieve a nominal 46.8 volts and a maximum operating voltage of 54.6 volts. The proposed TI BMS is connected to each cell in these series stacks, and thus each stack can be monitored, controlled, protected, and each cell in the stack can be balanced for optimum performance. These series stacks are then combined in parallel to achieve any desired battery pack power and energy capabilities. In order to not exceed the manufacturer's rated continuous discharge current of 15 amps for the particular cell chosen, a minimum of 10 series stacks wired in parallel would be required if the battery is going to power vehicle propulsion, as well as all on-vehicle subsystems. Here, an example battery pack of 3 parallel stacks of 13 series connected cells for a total of 39 cells is modeled to provide power for vehicle subsystems only and not providing power needed for vehicle propulsion, which includes all electric motors and their respective speed controllers. The 39 cell pack was modeled to determine the total energy discharged as well as runtime while powering a constant 273 watt load until the battery cutoff voltage was reached, which in this case is 32.5 volts. The 273 watt load is the power needed to supply the vehicle systems only, as described earlier, and doesn't contain a load required by vehicle propulsion. Note that in order to power a constant load, the current drawn from the battery must increase over time because of the decreasing battery voltage. Here, an example battery pack of 10 parallel stacks of 13 series connected cells is modeled to provide power for both vehicle subsystems and propulsion. As previously mentioned, a minimum of 10 parallel stacks are required so as not to exceed the 15 amp continuous discharge limit imposed by the manufacturer's recommendations of the cell. This 130 cell pack was modeled similarly to the 39 cell pack in that it was discharged at a constant load until the cutoff voltage of the battery was reached, but is instead powering a 5.79 kilowatt load, which accounts for the vehicle propulsion components as well as the onboard systems. Note the drastically decreased runtime as well as the more pronounced increase in pack current over time as the pack voltage drops. Although the constant loads imposed on each of the example packs differs greatly, and therefore a like-for-like comparison of the two packs cannot be made, the resulting data from both example battery models shown here illustrate the highly nonlinear behavior of lithium cells being discharged. More than 3 times the quantity of cells, and thus weight and volume as well, the larger pack only offers a 118% increase in capacity and only a 69% increase in stored energy. The 92% decrease in runtime can be attributed to the 2021% increase in power drawn from the 130 cell pack versus a 39 cell pack. I will now hand it over to Miguel to discuss the engine assembly model.
Thank you, Alex. As shown in Figure 20, this is an illustration of the powertrain assembly with all the required components. Starting from the right-hand side of Figure 20, the necessary components consist of a battery pack, a radiator, an ECU, a fuel pump, an oil cooler, an intake manifold, and then an intake air filter. In addition, from the left-hand side of Figure 20, more components are shown, such as a starter generator controller, a water pump, the ignition, an exhaust manifold, and then the exhaust. In the center, we have the SkyPower 180 rotary engine, and then the thermostat is shown on top. Furthermore, as shown in Figure 21 and 22, this is a visual representation of the correct placement of the powertrain design when installed inside the duct of the UAV. As shown, the engine is placed pointing upwards right below the ducted fan, following from the radiator and the battery pack towards the bottom. This powertrain design was assembled to minimize the volumetric space, allowing for better wind flow and thrust from the ducted fan. Additionally, the fuel pump must be placed at a higher level from the fuel tank since it is gravity bounded. Now, I would like to pass this presentation along to Ruben.
Thank you, Miguel. And now we'll be going over areas of future studies that we believe require some further research. These future studies consist of an alternative power source of a fuel cell, thermal efficiency analysis, its thermal effects on components, intake and exhaust design, cooling system, regenerative power, and hybrid flight type cycles. Initially, the fuel cell power source was considered because of its main advantages of zero to minimal harmful emissions, longer flight time capabilities, its fast refueling, and reliability and efficient. Here in Figure 23, we have a basic schematic of the proposed idea, but compared to its internal combustion engine for the 50-pound weight constraint and its corresponding volume, it was determined to be too big, too heavy, and too expensive. And for these reasons, it was ruled out. However, now for the increase in 50-pound weight limit to 100 pounds, it would be a viable source for power and should be considered upon further research. Here we have 5 readily available fuel cells on the market, and on the first column here on the left-hand side, some of the fuel cells have a number of parentheses next to them, indicating that we would need multiples of the fuel cell to satisfy the 3.5 kilowatt power demand. We have its dimensions with its corresponding weight and power to weight ratio, and its fuel cell sizing for 3.5 kilowatt power demand with its corresponding cost. Next, we have the thermal efficiency, which from the 100% applied fuel energy, only about 25% of the effective power goes into powering the UAV, 5% of it is lost due to friction, 30% goes into the cooling system, and 40% of it goes via exhaust gas. Now for the first design in hover demand of 7.5 kilowatts of power, this translated to 2.5 kilowatts of heat to the surrounding material via friction, 7.5 kilowatts into the cooling system, and 10 kilowatts to the surrounding material / components via the exhaust gas. Now this is important because from the 40% of the exhaust gas, you can determine the heat rate at which goes into the components that are exposed in the UAV, and can determine the temperature of this exhaust gas and determine if these components are worth keeping due to their operating condition, and see if the exhaust gas exceeds that limit. For example, here on the right hand side, we have table 19 of 6 onboard components with their operating temperatures. Now for our desired engine, we have the engine has a surface temperature of around 250 degrees Celsius. And the temperature of the exhaust gas can be determined from the thermal analysis that we previously stated. And thus, once it's determined, compare it with the operating temperature of these components. Now, figure 25 here, we have engine efficiency of the Wankel rotary engine and for a two-stroke air-cooled engine. Of the effective 25 to 30% that we discussed, we have a ratio here for a 15 kilowatt shaft power demand. It would equate to about a 35 kilowatt heat loss compared to the two-stroke air-cooled engine. With the same shaft effective power, it would correlate to about 45 to 60 kilowatts of heat loss. Now we'll pass it over to Brandon to continue the presentation.
Thank you, Ruben. In this slide, I wanted to dive into a regenerative power technique that we suggest needs more studies. In theory, it was designed to emulate regenerative braking. It is commonly used on electric vehicles by recapturing the kinetic energy from the disc of the wheels as the vehicle slows down. Now, how would that apply in flight? Well, interestingly enough, we propose a method in which you cut off power to the ducted fan when either descending or in forward flight. By utilizing the wind speed going into the ducted fan and the geometric properties of a propeller to our advantage, we can calculate the induced ducted fan RPM and calculate how much power can be regenerated as well as its thrust. Some important things to highlight here are, as the angle of flight increases, wind speed, ducted fan RPM increase, and the power regenerated increases as well, which indicates a coefficient of performance greater than 1, except for at a 20-degree flight. Now that we understand the idea behind this regenerative power technique, some things that deserve further analysis include, number 1, using wind turbine theory combined with the ducted fan geometry and losses in the system to find what the true extraction of regenerative power are. Number 2, the rechargeability to battery methodology, in which one finds the recommended spooling times and at what flight scenarios provide the most feasible option. This is because as the ducted fan reduces its velocity, it also reduces the thrust it's providing, which would ideally increase the output power requirement from the outer propellers. The wings of the UAV may provide enough lift at higher angles to validate this technique, which is why it needs further study. Now, keeping our focus on what's going on inside the duct, the next suggestion includes further studies in psychoanalysis of the inner duct. Number 1, finding out how the thrust is affected by the cross-sectional area taken up by the powertrain and how the heat affects the sensors around it and the vehicle frame itself are vitally important. Number 2, being able to use the CFD in SolidWorks or other programs by integrating the powertrain inside the flight vehicle would be a great way of optimizing the design and making sensible decisions of placement. In this slide, I wanted to talk about the designs that will impact the engine performance. Number 1, the intake and exhaust design will allow one to tune the engine and optimize a BSFC and power demand of choice. Number 2, being that the previous studies in psychoanalysis were completed, one would be able to extrapolate that data and design a custom cooling system that would allow for the engine to run at its optimum conditions. Finally, I wanted to suggest acquiring a test asset from SkyPower. This would allow the team to understand the powertrain functions and performance parametrics, which include thermal and vibrational information that we do not have, as well as the powertrain component placement for sizing dimensions inside the duct while taking into consideration the performance metrics. Now I'll be passing it off to Anthony to conclude.
Thank you, Brandon. All right, next we'll be going to the summary and conclusion section of the presentation, where we will be discussing about the functional requirements of the UAV and the cost and weight table for both designs. Here is the table for the functional requirements for the second design again. Some things to highlight are that since there is a change in the overall weight of the UAV, there has been an increase of volume inside the duct and the power demand range also increases. With this weight increase, the powertrain subteam was able to meet with the constraints. Here is the weight and cost table for the first design. This table showcases the components with their respective brand, power, weight, size, and cost, along with the total cost and weight of the whole setup. One thing to note is that the asterisk is just to showcase a price approximation. The total weight of this design is about 47.5 pounds, while the total cost is around $36,000. Table 23 is the weight and cost budget for the second design. Few things to point out when comparing with the first design is that we have changed the engine, the generator, the electric motor for the micropropellers, the battery pack, and then there's an increase of the volume of the fuel. The total weight of this setup is around 61 pounds, and the total cost is around $57,000. To sum everything up, the team has made a power split architecture design, which allows rechargeability done by the engine's generator. We are able to increase the flight time, And we have made multiple power allocations utilizing the battery and the generator for the UAV. The Wankel rotary engine we picked can provide better fuel efficiency at high power outputs. It has a greater power to weight ratio than a fuel cell engine or a two-stroke engine. It has a small cross-sectional area which can fit in the duct of the UAV. The battery pack that we decided upon already has a battery management system and contains a high discharge current, but with a fast recharge time. Based on the hover flight analysis, the results show that using a hybrid cycling method will provide us power for all UAV components. We used a 50-50 fuel to battery ratio, meaning that the battery is being discharged until it reaches 50%, then having the UAV run on fossil fuel while recharging the battery back to 100%. This cycle can be done 21 times, which let us achieve a flight time of 7 hours. We have made a powertrain design where the iteration was done on SolidWorks. Each component was specified with respect to the weight dimension and estimated cost. And we have done trade studies where we look into different architectures to showcase different options and study how to use the gearbox to convert the output energy from the engine to rotational energy for the ducted fan. And that concludes our presentation. Thank you all for watching.